Hello and Assalamu alaikum. In this video, we will be doing a lot of things, one of which is the basics of the CFD. So, in the basics of CFD, we will be doing a pipe flow simulation, which will cover the basic CFD principles and will guide you through the process of CFD. So, this is a very basic tutorial, and you should follow it just for the purposes of learning CFD basics. So this is the first video in the series of CFD basic tutorials. These are very basic tutorials and used for understanding of the CFD flow simulations. So let's get started into the video. So let's open Workbench. So go to the start menu and select Workbench. I have ANSYS 19.1. You can have any student version or any version. It will be similar, but in the advanced versions, the workflow is a little bit different. So if you have ANSYS 19.1, you can follow it very quickly. So this is the ANSYS Workbench. On the left side, you can see a toolbox. So it contains all the systems that are to be used in the ANSYS, from the static structural, from the harmonic analysis to any analysis that you are being doing in the Workbench file. This is the project schematic. Now this shows how your systems, the design systems, are related to each another. And these are the basic toolbars from which you can change the backgrounds and whatever. So from here we are interested in the fluid flow. I am going to just click on it, drag it, and put it over here in the create standalone system. This will create a system of ANSYS Fluent in which the geometry is related to the mesh is related to the setup, and the setup is related to solution and results. So this is a pre-made system. You can also make individual systems for this, but for this it is not covered in this tutorial's scope. So the basic things are, we will create a geometry, we will mesh it, we will apply boundary conditions on it, and then we will post-process the results. So whatever you do in the ANSYS Fluent, first of all save it. Otherwise your temporary storage will be full. So to save it, go to File, Save As. Now I am not going to show you how to save a file. This screen will be blurred, but you can save it into any file which has a little bit storage. And name as tutorial 1. Okay, so as we have saved our file, now let's proceed to the geometry. As the geometry modeler is opening, oh sorry, I didn't explain you how to open the geometry modeler. So you will just click on the geometry, right click on it. You can either edit, make the geometry in space claim by default, or go into the design modeler, and here will be your design modeler. The second option is of design modeler. So this is our design modeler over here. Now this graphics is a little bit difficult if you are coming from SolidWorks perspective. So over here, this is the tree outline, and this is the graphics zone where you will see your body. These you can see over here these are the selection modes. This whole is the selection modes that we will be using. These are named as selection filters. You can either select single select or box select. This is a point, edge, surface, and then body selection. This is our design modeler. So as we click on the XY plane, we can see our origin. Origin is something from where you can start drawing something. So this is the origin. From here you can rotate your stuff, your views and many things. This circle which you can see is for the isometric view. You can have an isometric view of your design body from here. So our aim is to simulate a pipe and see the no slip condition in the ANSYS Fluent. This is a very basic thing that we will be covering in this video. So click on the XY plane, then look at. Now what mistake that everybody does in the ANSYS is that they don't set up the units first. Always set up your units first. So from the toolbar, select millimeter. Go to units, select millimeter, because it is very convenient for engineers such as us to do in the millimeters. We can, if ANSYS had bananas, we could also select the bananas. These we selected millimeter, the MKS system. Now you can see our units over here in the scale are in millimeters. This scale determines what are you seeing over here in the body. If I will draw a line from here to here, that will be of 60 mm. So you can judge the size of your whatever you are creating through this, that what will be the length without measuring it. So we have looked at, we have gone to look at. Now we will sketch it, but there is no open option over here. So we will go to sketching from here. This will include us many options over here. Now, as we have gone into the sketching, we will draw a rectangle. A pipe, when we see it in 2D, is a square or a rectangle. As a pipe has a length that will be greater than the diameter, we can see it as a rectangle in the 2D spectrum. So we are going to draw a rectangle. Now we can draw a rectangle around the origin, but in the CFD post, there will be some problems for that. So we will draw from the origin into the positive quadrant and stop anywhere. Now what we are going to do is utilize ANSYS capabilities. So one line is going to be the axis and we will be only using one wall. This is known as symmetry. So this wall will be used to see the velocity profiles for the flow. Now this wall will be how much higher depends upon our diameter of the pipe. So I am saying that the pipe diameter is 0.2 meters, which is 200 mm. But since we are using symmetry, I am going to say this is 0.1 meter, which is 100 millimeters. And the pipe length. What will be the pipe length? Okay, if you are confused how I am creating the dimensions, so simply go to dimensions. We were first into the draw, select dimensions from here, and then go into the length distance. This is very easy to do. You can also select vertical from here, but I will choose the length distance from here. Now select any one line and select the other line to create a dimension. So if you have understood it till now, very good. Please subscribe to my channel. So we are going to create a dimension over here. So two dimensions have been created, the length and the width. So now we will give its value. So we cannot give its value from here or here. We have to go into the details view. And from details view, there will be something known as dimensions over here. Dimensions over here. There are two dimensions over here. Since we created two dimensions. So now L1 is this. So our diameter of the pipe, which is now in symmetry, will be 100 mm. And our length will be around 8 meters, which is 8000 mm. If you have your view has been subjected, you can uh, use your mouse wheel. If you're using ANSYS Fluent or any design software, please use a mouse. So this is the cross section of our pipe. But now, as you can see that this is only 2D geometry. It has no mass or anything. So what we will do is that we will create a concept that these are not lines. This is the surface. So we will use the concept to go to the toolbar, see up in your ANSYS Fluent. There will be something known as this is the design modular. See, there will be something as concept, and then lines from sketches. We don't need a line. We need surface. So we will be selecting the surface one. So surface is from sketches. So a surface has been created in the tree video tree outline. So I will select the sketch that we created. Okay, so we created an sketch on our XY plane. So the sketch will be under the XY plane. So I selected it from the tree outline and apply. So the sketch has been selected now. What we will do now? Why isn't the sketch showing? Just go to the electricity symbol over here and click on generate. See this? Click on generate. Whatever things will be not loaded will have an electricity symbol over here. Now let's resume. Now you can see that the surface has been grayed down. It has been filled with a gray contour. Now what we will do is identify that this surface that we have been created is a fluid. So from here, part 1 body, select the surface. Now in the details view, you can see that there is fluid and there is solid. Now select fluid. Now what will happen? The design modular will consider this surface as fluid. So okay, our geometry has been done. Now we will proceed to the mesh. Now to go to a mesh, first of all, close your design modular. Now this is the most important step. So just save your file. If you think that the video is too long, this is just for a conceptual. This is a conceptual video, and it is for the beginners, not for the extreme experts. So now go to the mesh. You can see that now mesh has turned into a recycle bin symbol, which mean it needs processing, and others are question mark, which means the data has to be fed from the mesh to the setup. Now double click on the mesh, which will open your meshing, which has a similar experience to the design. Okay, so this is the meshing. Now I will click from here in Z direction. Now I can see my pipe, which is of 8 meters length. Now, first of all, the first step that I will be using is to go to this selection filter and select H, because the first step that I will do is to name from where my fluid will enter, from where the fluid will exit, which is the wall, and what is the axis. We have to tell the ANSYS Fluent in the later steps by in the meshing section that this is an inlet, this is an outlet, this is a wall, this is an axis. So to do that, we will select the line in a meshing, then right click on it. Then there is an option over here which is create name selection. You can simply click on N. This is the written over here and this will appear. Now I am saying that this will be the inlet. So inlet velocity, because fluid will have some velocity. Now let's go to the other end and see. Click on it, right click, do it, and then create named selection. This is our outlet. This is the pressure outlet. Why? You will see that in the ANSYS Fluent setup settings. It is easier to just do outlet. You can do outlet as well. Now the upper one will be the wall. Right click on it, create a name selection and set it as wall. Now the bottom one will be your axis. Right click on it, create a name selection and set it as wall. So now we have created our named selections. Now the time is for the mesh creation. Now the mesh creation is a very important step. Now as we want to study the flow over here on the wall, so we want our mesh to be of very fine thickness over here. The mesh should be very fine over here. We are not interested in this flow. We are interested what will be the flow over here. So we need to create a mesh that will have the minimum mesh size over here and then proceed to be larger size. For this, follow our tutorial. We are going to tell you how to do that. So from the tree, click on mesh, right click on it, insert, then from here you select sizing. Now make sure that you are selecting an edge from here. So now select this edge, this one, the inlet one. Select it, click on the geometry. You can click on it and then select as well. Okay, now we have selected this. Now I want this to be in many pieces, but it should be over here. Now if I just do any element size and then I go to number of divisions. Now as I increase the number of divisions, you can see our line has been divided into divisions, but these are equal divisions. We don't want equal divisions. I am just going to put a random number over here, which is 100. We are going to create 100 divisions for an example, but you can see these are equal, but we want that our divisions are more on the inside side of the wall. So we will make sure by creating a bias. This is a bias over here in the advanced menu. If you don't have the bias, it is under the advanced setting. Make sure that the behavior is hard because this is a 2D, and create a bias. And which bias you will select? The first one. What will it do? We will see. Now the bias factor, I will be selecting 10. 10 as the bias factor. Let's see what it has done. It has created a bias on this side. Do we want a bias on this side? No. So which will be better? I think this one will be better. Okay, so now you can see that the divisions are more over here. But you can see one thing, that there is some overlapping over here. So just reduce your number of divisions if you see any overlapping, because this can create some issues in your mesh. This we have done the meshing in the inlet. So now we will create a mesh over the outlet. You might be confused that how I am doing this. So just press your control key, the middle mouse key, and then slide your mouse. Then you can go over here. And how I am zooming, I am just going for my middle mouse key. Now select this also, and then select this, create a sizing over from here, mesh, right click, and then insert a sizing. We have created a sizing. Now let's go to number of divisions, and what we have selected over here, we will be putting the same number over here, which is 60. And now let's change it to hard, as we selected before. The second one, should we select that? Let's see. Bias factor the same as 10. So let's see what happened. Oh, see, this is how ANSYS depicts your geometry. Now this is viewed as a negative vector, so the bias is applied to the bottom. What we have to do, we have to create a reverse bias. So we will just bias type and select the first one. Now you can see that the bias is over here. So that means that there will be more divisions over the wall and less divisions over here. If you increase your bias factor, what happens? There will be more saturation on the edge and less saturation over here. If you are going for a mesh of 20, bias of 20, you can see how much it is condensed over the edge. I am going for 10, but this is what it means, and we are interested in what it means rather than just clicking on the buttons. Also create another, we have to also create divisions for this edge and the bottom edge. So insert sizing. Now this time we have to select two edges, because both of them will have equal and both of them will have no bias in it. So selected both of them by pressing the control key on your keyboard and then apply. We have selected two edges. Now as we selected in the bias 100 divisions and 60 divisions and 60 divisions, we will go for 100 divisions over here, which will be equal, because we don't want to see the flow over the inlet, or specifically we want to see over the wall. That's why we are creating equal divisions over here. So 100 divisions will be okay, I think. We can also go for 200 divisions, but nevertheless, you can see 60 divisions, again 60 divisions, and then 100 divisions. Should we increase our divisions? You can increase your divisions, but it will have no effect over your results, because when you will see results and then change your meshing, if the results vary, then you should improve your mesh. If it doesn't vary, it means that your mesh is perfect. Now let's generate the mesh. You can simply click over here to create the mesh, or click over here to generate the mesh. See, we have took time to understand these things. Now this is not what we desire. This mesh is not what we desire. So we will click on it, then again right click on it, insert. Now we have to insert a mesh control. So just go from here, mesh control, and then select face meshing. Now we have to select this face, apply, and voila, our mesh is now perfect. So there seems to be a problem over here that our so let's see what the problem is. The problem is that our these are not perfect. So what we can do, or what we should do, is to apply mesh again of this sizing, or increase some divisions over here. I'm going for 200 divisions, and let's see what happens. Defeaturing tolerance. There is an error. There is some error. Now what will be the error and how do you calculate it? No, any tutorial teaches you that. Only tutorials teach you how to cope up with the solutions. We will teach you that how to deal with problems. Dealing with problems is very difficult. So let's see what we have done wrong. We have not changed our behavior into hard. Let's just change the mesh again. Now let's see what are the results. See, these mistakes teach you more than what you learn in the class. Mistakes do mistakes. Too many mistakes. See, our mesh only was not hard, and our mesh was like going tiltways. So as we hardened it, it became straight. Okay, so we have generated a mesh. Okay, so that's a good mesh. You can see that there are more number of divisions in the upper side and less on the lower side, because we have to see what are the mesh over here and not what are the results over here and not over here. So we have generated a good mesh, and this is enough. Now there isn't some error over here that specified defeaturing tolerance was found to be larger than the specified size. Now how to deal with this solution, this problem, is to just change the divisions from here. I will change it to 20 with divisions, also in the second one, and you will see that our problem is gone. Let's change this as well, change it to 100. Let's see what happens. This error is related to these and these. There is a perfect ratio. If there is a perfect ratio find between them, then this error will be reduced, but it will have no any effect on your results. So keep that in mind. So I have changed the settings back to 60, and then over here it is 100. So keep these settings only. Whatever you have done, I was just teaching you what this problem means, because we need meaning. What are we doing? Why are we doing? Now we will close it to just save some memory of our laptop. Now make sure you update it so that the information is conveyed to the setup, the solution, and the results. And make sure that after your mesh you save your file. Save time, save water, save your file. Sorry for the video being so long, but because I have to discuss the important things in the ANSYS Fluent, so we have to wait some time. Thank you for observing the time for and watching the video. Now I will file, save water, save your file. Now let's double click on our setup. Now there are some settings over here. The ANSYS Fluent has already identified our dimensions at 2D. Just select double precision. If you have a parallel processing system or a very hi-fi system, you can go for parallel processing. It will help you to do simulations very faster. Since we don't need it, we are not going to choose it. Now this is our mesh. So something that I missed in the meshing was to check the mesh quality. So if we have missed to check the mesh quality in the ANSYS mesh, we can check it also from here. Just go check. Yes, mesh is okay. What is the mesh quality? Aspect ratio is -2 and some are on 1. Minimum is 1 and the maximum is also 1, which is a good quality. What I mean, you can see that the minimum mesh quality or the minimum orthogonal quality is 1, because this is a quadrilateral system that we created, so it will be of the order 1 and it is the best mesh. So there are various things that you can do over here. Now we have a solver. Now what solver means, that what type of solver that our ANSYS Fluent will use, pressure based or density based. We will be using a pressure based solution for this. Also velocity formation. What will be the velocity formation? So this will be an absolute velocity formation, because we don't want our particles to be faster than the other particle. Now this is a steady state, which means that there is no time involved. If this is a transient, which means that there is time involved, and in the transient we do have animations. We will learn it later in the tutorials. Now axisymmetric and axisymmetric swirl. Swirl, we will also learn it in the later tutorials. Subscribe to my channel for that. And now go to the axisymmetric. Because we have an axis, we will choose axisymmetric. If it was only a single surface, you go for the planar. But since we have an axis on which we are using the symmetry function, select axisymmetric. Now models. There are many models over here which will be discussed in the later tutorials. We will be selecting, you can see over here there is a viscous. Since we are only dealing with the flows, we will be selecting the viscous model, and there are 3 main models that can be used over here, which is the K epsilon, K omega and laminar. Since laminar, we are not dealing with laminar flows, we are dealing with turbulent flows. We will be going for the K omega. We will be seeing the laminar profiles as well. So let's go for K omega. K epsilon is also a good model, but because of the wall treatment problem in that K epsilon formula, the equations, sorry, I called it formula, for the K epsilon equations, the problem is that it assumes something on the walls. That's why we use the near wall treatment function from here, enhanced wall treatment, to do that. But we are going to just go for the absolute best in this case, which is the K omega SST model. which is a mixture of K epsilon and K omega. Okay, so we have selected the K omega SST. Now from materials, in the materials over here you can see this is air. Now let's suppose that our density is 1 and our viscosity is 0.3, and then close it. You can change the properties like this. I am telling you, you can use also the already made things, but since we are doing some things, now these are the cell zone conditions. Cell zone conditions can be described as what material will be used for the simulation or what method will be used. So since we are using air, the material is air. Okay, now let's do the main thing, which is discuss the boundary conditions. Now I am double clicking on it. Now click on the inlet velocity. Now see the type, that what is our inlet type. The type is of velocity inlet. We can edit it. Now you can see here it is the velocity inlet. What inlet will be providing? I am going to provide it 1 meter per second speed, and the turbulence. Now what is the turbulence? Now according to what turbulence you select, it will give the inlet pressure and the inlet things in the inlet turbulence. We are using the pipe, so there are many options. So since we are using pipe, we have the intensity and the hydraulic diameter. We have the diameter of the pipe, which is 0.2 meters. So let's go for the intensity and hydraulic diameter. Change this to 0.1 and change this to 0.2, and then OK. Velocity magnitude 1, intensity 0.1, diameter 0.2, and OK. Now what we will the next thing that we will be doing is give an axis. We will describe this as axis. So if we haven't displayed it, so let's display this wall. Yes, this is the wall 1. We want this wall 1 to be our axis. So go to the boundary conditions, select wall 1 to be an axis. Okay, and this should be a wall. This is the upper one. Go to general, display. The upper wall will be shown. If you have missed your things, you can go over here. This is our upper wall, this is our lower wall. You can see over here. I am going to display everything. Display, close. Now we have described our boundary conditions. Let's also look at outlet pressure and edit it. You can see this is a pressure outlet. The gauge pressure is 0. Now what does this mean that our gauge pressure is 0? It means that the outside pressure. Now how do we measure a pressure? When we measure the pressure through a gauge, we add our atmospheric pressure with that absolute pressure in that gauge, so that we can get the original pressure that is in the pipe. So since the outside pressure or the surrounding pressure is 0, then whatever pressure that we will be seeing will be also true. That is this meaning of what we select as 0. This is specification method. You can also change it in the here, but here it is not very it is not to be selected over here. We can do it, we should do it the same settings, 0.1 and a diameter of 0.2. You can do it, there is no harm in doing this, but this will have some effects. I am again saying that this will have some effects on our results. Now there is reference values. Now let's go to the reference values. So these reference values help in the later processing. So always compute from whatever the wall you are going to be studying or whatever we should do. So I am just going to compute from inlet because this is for the y plus, but we don't need y plus over here because we are doing k omega SST, which is very accurate over here. So we have done it, and now let's select our solution settings. Now click on the methods. Now from the methods, please do a thing that select the second order upwind, because by using second order upwind we actually do a lot things to make our simulation very accurate. Now controls, these are the pressure controls that will be used. We can make the momentum 0, the turbulent, we can change these settings, but I am not changing it. Depot definitions, let's do some things. Go to the monitor convergence criteria. So for me it is not opening. So you have to do the thing that in the convergence criteria, for all of the things, whatever it appears, change it to 1e minus 6. What will happen? The convergence criteria will be changed for the ANSYS Fluent because it is currently 0.01. So it will be changed to 1 minus e6, which will help us doing it. Now let's go to the initialization. Initialization does something that it fills the inlet mesh boxes with certain things, and then as you proceed it moves forward. It is like we are initializing our solution, we are initializing the inlet with some liquid, we are filling some liquid into the inlet that will be flowing through the meshes in when we solve it. So turbulent kinetic energy, radial velocity, axial velocity. Now let's run the calculation. Now change, initialize it, compute from inlet velocity, initialize it, and then go to run calculation, and the number of iterations will be 1000, and go to calculate. We will be calculating Thank you for watching if you are watching till now, and please subscribe to my channel. Now you can see these are the residuals. Whatever you are seeing over here, these are the residuals. Means whatever the criterion will be, it will show the K, the continuity residual. Now the solution has been completed. Now I will not go much into the depth of the post processing in this video, which is not our scope over here, but there is a tutorial of ANSYS. I will be sharing it on the screen, you can see on the screen, but that has covered the post processing very efficiently. This is also related to that, so do check that out. Now what I will do, I am interested in the vectors of the velocity and the boundary conditions. First of all, let's create a contour. Now I have just double clicked on the contour. You can change the velocity contour name. I'm going to say velocity profile. Let's see the velocity and just select the option field. Node values and global range has to be discarded. Save the display. You can have a fair idea from here what your velocity profile will be. The blue shows there is no velocity and the red shows maximum velocity. So just go for the vectors. In the results, go for the vectors, select velocity, velocity magnitude. Just don't select global range. Go to auto range, compute, and save display. So this is the velocity profile of our solution. Now whether it is a turbulent profile or whether it is a laminar profile, compare to the picture over here and tell me in the comments what this profile means. This profile is related to whatever velocity we put it in the initial stage. So this seems to be fairly laminar. No, it seems to be a turbulent velocity because it is converging at all. But as we can see that in the laminar, it will converge very slowly. I am going to show that by just changing the initial conditions. Now go to the boundary conditions and let velocity change it to 0.1 and initialize it. Make sure that you initialize it. Initialize it. Okay. Take a screenshot. Okay, done. So I'm going to, we have initialized it. I'm to go to do it again. I'm going to do it again. Now run the calculation again. And let's see what the velocity profile will be. We are interested in the velocity profile. We have discussed many things in this video. So please subscribe because it is a long video and it took a lot of time to me to create this video and edit this video. I'm going to also show you some very funny things. Go to CMD, then type CURL live ASCII.live and then backslash. Can you hear me? Congratulations, boys, girls, you have been rickrolled. Also, our calculation has been completed. It has actually converged. You can see that 1000 has been not completed, but our calculation has been converged. Now let's see the velocity profile. See, that was a turbulent profile. This is a laminar profile. So this is how you see the profiles. What is the importance of seeing these profiles? Now this is whatever we have done is related to the other things that we will be creating, like inflation. Now why we create inflation is to see what is the velocity profile around that object. So this is just a simple tutorial in the first tutorial in our series that has, if this gets 1K views, I am creating another one. So this is our velocity profile. I hope you liked it. If you like my funny jokes and the way I teach, please subscribe to my channel. There will be many videos over here, and I make sure that it will be longer. I am not saying that it will be any shorter, because it will be longer. It will reach 1 hour, 1.5 hours, and I think that you will be watching it. Please watch my videos. Give me money. So please subscribe to my channel.